Curves defined by parametric equations. Parametric equations have the form x equals f of t and y equals g of t, where f and g are given functions and the parameter t typically varies over a specified interval, such as a is less than or equal to t is less than or equal to b. The parametric curve described by these equations consists of the points in the plane that satisfy xy is equal to f of t, g of t for the t values in that interval from a to b. Now, one thing that's important about a parametric curve is that it has direction. We sort of think about t, often we kind of call it the time, right? So time moves in one direction. We think of the t moving in one direction. And as t moves in the one direction, the points on the curve move in that direction. So when we draw a parametric curve, we want to put arrows signifying the direction of the curve. So for example, let's sketch the curve defined by x equals 1 plus t and y equals 5 minus 2t. So in this case, we were not given any, we were not told any restrictions on the parameter t. We weren't given an interval. So I'm just going to choose some values for t. And so it might be helpful when you're asked to do this to set up a chart, put t in the first column and then x and y in the second and third columns respectively. So I'm just going to choose some values for t. I'm going to go from -3 to 3 by ones. And then what I would do is substitute into the x equation each of those t values. All right, so if x is 1 plus t, then when t is -3, this would be -2, -1, 0, 1, 2, 3, and 4. And y is 5 minus 2t. So if t is -3, 5 minus 2 times -3, that would be 5 plus 6, that's 11. And similarly, then we would get 9, 7, 5, 3, 1, and -1. Now the points that you would plot would be the x and y coordinates. So we would have the point -2, 11, -1, 9, 0, 7, 1, 5, 2, 3, 3, 1, 4, -1. And it appears that this is a line. So I'll draw the shape that looks like a line, and it has direction. So we would put an arrow in that direction. All right, signifying the movement. As mentioned in the introduction of this section, sometimes the parameter is restricted. In general, if we are asked to work with a curve given in parametric equations, with a is less than or equal to t is less than or equal to b, we say that it has a terminal point at f of a, g of a, an initial point at f of a, g of a, and a terminal point at f of b, g of b. So let's consider the curve x equals 8 cosine t, y equals -4 cosine t over the interval 0 to pi. As I did before, I'll set up a chart with t, x, and y, and I'll choose a few values for t. So how about 0, pi over 4, pi over 2, 3 pi over 4, and pi. So there are a few t values. So now let's see, the cosine of 0 is 1. So then x would be 8 cosine 0, 8 times 1 is 8. The y coordinate would be -4 cosine 0. -4 times 1 is -4. The cosine of pi over 4 is root 2 over 2, which is about 0.7. So let's see then, 8 times the cosine of pi over 4, 8 times 0.7, that would be about 5.6. And negative 4 times 0.7 would be negative 2.8, approximately. Now, pi over 2. The cosine of pi over 2 is 0, so this would be 0 and 0. 3 pi over 4. The cosine of 3 pi over 4 is negative root 2 over 2, and so that's about negative 0.7. Multiplying that by 8 would be negative 5.6. Multiplying that by negative 4 would be positive 2.8. And finally, for pi, the cosine of pi is negative 1. Multiplying that by 8 would be negative 8, and by negative 4 would be positive 4. And so again, we have our ordered pairs. So let's see, we have 8, negative 4, 5.6, and negative 2.8 would be about here, 0, 0, negative 5.6, 2.8 would be about here, and negative 8, 4 would be about here. And so it looks to me like we have a line segment here, not a line, because it has an initial point and a terminal point. So it looks like we have a line segment with initial point at 8, negative 4, and terminal point at 8, 4. And we do indicate the direction. I'll put an arrow indicating the direction. And that's it. It doesn't go beyond those points. So here's another exercise, and this would be a good one to try on your own. So if you'd like to do that, now would be a good time to pause. We're asked to sketch the curve x equals t minus 1, y equals t cubed plus 1 on the interval negative 2 to 2. So I'll set up my chart with t, x, and y, and I'll just throw in some t values and find the corresponding x and y values. All right, so x is the t coordinate, or the t parameter subtract 1, so that would give me negative 3, negative 2, negative 1, 0, and 1. And the y coordinate is given by t cubed plus 1. So let's see, negative 2 cubed, that's negative 8 plus 1 is negative 7. Negative 1 cubed is negative 1 plus 1 is 0. 0 cubed plus 1 is 1. 1 cubed plus 1 is 2. And 2 cubed plus 1 is 9. Plotting these points. Let's see, I'd have negative 3, negative 7. Negative 2, 0. Negative 1, 1. 0, 2, and 1, 9. Now, this curve is only defined over over the parameter negative 2 to 2. So in drawing the curve, it has an initial point and a terminal point and does not extend beyond those points. And notice I'll draw a couple arrows to signify the direction. Let's consider one more exercise here. We're asked to sketch the curve defined by x equals 6 cosine t, y equals 6 sine t on the interval 0 to pi. All right, so I'll again set up my chart with t, x, and y. And let's see, like I did before, I'm going to use 0. I'll use pi over 4, pi. 3 pi over 4, pi over 2, 3 pi over 4, and pi. Alright, so now let's see. The cosine of 0 is 1, so multiplying that by 6 would be 6. The sine of 0 is 0, multiplying by 6 would be 0. The cosine of pi over 4 is root 2 over 2, which is about 0.7. So 6 times 0.7 is about 4.2. The sine of pi over 4 is also root 2 over 2. And so this would also end up being 4.2. Pi over 2, the cosine is 0. So 6 times 0 is 0. The sine is positive 1. So 6 times 1 is 6. 3 pi over 4, the cosine is negative root 2 over 2. So that would be about negative 0.7. So this would be a negative 4.2. The sine of 3 pi over 4 is positive 0.7, and so that would be, again, 4.2. And at pi, The cosine of pi is -1, so 6 times -1 is -6. And the sine of pi is 0, so 6 times 0 is 0. All right, plotting some points here. Let's see. We would have 6, 0, 4.2, 4.2, 0, 6, -4.2, 4.2, and -6, 0. Well, that looks okay. What if I found some other, let me find one more point, or two more points. What if we had, say, pi over 6? What if my parameter was pi over 6? Well, the cosine of pi over 6 is root 3 over 2, which is about 0.87. Multiplying that by 6 is about 5.2. The sine of pi over 6 is 1/2, and multiplying that by 6 would be exactly 3. So when t is when t is pi over 6, now understand that that should be, here, if we're looking at the table. And so we would have another point, 5.23. 5.2 and 1, 2, 3. That would be about here. And similarly, if we were to look at 5 pi over 6, we would get -5.23. And so if I look at those points, and we could find more points using other special angles, it sure does look circular in nature. And so in fact, we get this semicircle. All right, and in this direction. And this is actually an important parametric curve. In general, the equations x equals a cosine t, y equals a sine t, yields a circle with center 0, 0 and radius a. Now here we see that we only got a semicircle. Well, it's a semicircle because we only went from 0 to pi. And if you sort of think of the period of the functions, the period is 2 pi. And so what we would expect is that it would complete the entire circle over 2 pi. And that's true. In general, x equals a cosine t, y equals a sine t yields a circle with center 0, 0 and radius a, traced counterclockwise as for t or 0 to 2 pi. And so since we only went from 0 to pi, we only got a semicircle. All right, let's keep that in mind. We're going to use that later on. We can plot parametric curves on our graphing calculators. We just have to adjust the mode of the calculator and then use it correctly. So here we're going to do something a little fancier. And this would be very difficult to sketch by hand. We're going to sketch the curve x is t plus 2 sine 2t, and y is t plus 2 cosine 5t over negative 2 pi to 2 pi. All right, so on the calculator, what we'll do is turn it on, of course, and you have to go into the mode. So hit the mode key. And what we want to do is change, right there on graph, it's in function mode. Press to the right, and we have our choices, and we'll switch over to parametric mode. We hit enter to save to parametric, and then we have to hit one more time to save that we've changed the mode. All right, now if you go to your y equals screen, you'll see it's a little bit different. It asks for an x and a y, right? You see xt1, yt1. So in xt1, I'm going to type in t plus 2 sine 2t, and close that off and hit enter. All right, and my y of t is t plus 2 cosine 5t, and close that off and hit enter. All right, so I've got that in. Let me look at the window. So now in your window, it asks for a t minimum and a t maximum. And so here we want to start at negative 2 pi. So negative 2 pi, hit enter, and we want it to finish at positive 2 pi. And for x min and max, and t step, I've got it at 0.13. That's how often you want it to plot a point. That's fine. Just leave that alone usually. For the x min, I've suggested negative 6.5 to positive 6.5. And for the y's, I've suggested negative 8 to 8. So notice this is a little bit different than your standard window. You have to tell it, you have to also give it a range for the parameter, and then a window for the actual screen. All right, I'll hit the graph button, and we get this fancy looking curve. Like I said, this would have been very difficult to plot by hand. Let's just look at the circle real quick. Let me go to my y equals screen and let me plot. What do we had? We had 4 cosine t, or no, it was 6 cosine t and 6 sine t. So 6 cosine t and 6 sine t. And let me just change the window. Let's just go like I did in the exercise. Let me go from 0 to pi first. And I'll graph that. And it looks like an ellipse. It doesn't look like a semicircle, and that's because of the way we have the window set. If I zoom to a square window, zoom square, it should look more circular. All right, and I certainly do see a semicircle there. And just to verify what I said earlier, let me adjust the window one more time, and let me make the window go from 0 to 2 pi. And what we'll see is that this will trace counterclockwise an entire circle. Sometimes, when we're working with a parametric equation, we would like to be able to eliminate the parameter and write the Cartesian equation, so just in terms of x's and y's. So here we have x equals the natural log of t and y equals the square root of t. So a Cartesian equation would just be in terms of y and x. So sometimes we can simply rewrite the equation and solve for t. So if x equals the natural log of t, remember the natural log is the log base e. So if x is equal to the natural log of t, then t is equal to e to the x. And so then I can take that e to the x and I can use it to replace t in the other equation. And so then y would equal the square root of e to the x. Now, notice we've changed this from a parametric equation to a function, right? Y equals the square root of e to the x. Now, we had this on the parameter. We were told that the parameter had to be greater than or equal to 1. So now look what that does. If t must be greater than 1, then x of 1 would be the natural log of 1, which is 0. And since the natural log is a 1-to-1 function and increasing, what that tells us is then that x must be greater than or equal to 0. So let's look at another exercise. Here we have x equals 4 cosine theta and y equals 5 sine theta, and we're asked to eliminate the parameter to find the Cartesian equation of this curve. You might look at this and say, well, is it a circle? It's not a circle. I know it's not a circle because the coefficients are not the same. In fact, this would turn out to be an ellipse since the coefficients are different. All right, we're not going to focus on that right now. Instead, we just want to find the Cartesian equation of the curve. Well, we could use the approach we did last time and try to solve for the parameter. In this case, the parameter is theta. So I could say that x over 4 is cosine theta, and so then theta would be cosine inverse of x over 4. And then I can substitute that into the other equation. So then y would equal 5 sine of cosine inverse of x over 4. Well, cosine inverse of x over 4, if we sort of think of that as the angle, right, this was our theta, and the cosine is x over 4, so adjacent over hypotenuse. Pythagorean theorem gives us a 16 minus x squared. And so then the sine of theta, y would equal 5 times the square root of 16 minus x squared over 4. And that's acceptable. It's not a very normal form of the equation, but it'll work. Let me show you another approach. So notice that x over 4 is cosine theta, and working with the other equation, y divided by 5 is sine theta. Now, for each of these equations, I'm going to square both sides. So then x squared over 16 is cosine square theta, and y squared over 25 is sine square theta. And I'm going to add the equations together. And so addition of the equations yields x squared over 16 plus y squared over 25 is equal to cosine square theta plus sine square theta. And that cosine square theta plus sine square theta should be, you should be familiar with that. That's 1. X squared over 16 plus y squared over 25 is 1. Which you may recall as the equation of an ellipse. In a standard form, you hopefully saw that back in a pre-calculus course. Parametric equations are often used in higher level calculus courses and physics courses. And so here's an example from motion. If a projectile is fired with an initial velocity of v0 meters per second at an angle alpha above the horizontal, and air resistance is assumed to be negligible, then its position after t seconds is given by the parametric equations. X is equal to v0 cosine alpha t, y is equal to v0 sine alpha t minus 1/2 g t squared, where g is the acceleration due to gravity, 9.8 meters per second square. So if the gun is fired with alpha is 30 degrees and v0 is 500 meters per second, when will the bullet hit the ground? All right, so the gun's fired at a 30-degree angle to the horizontal at 500 meters per second. When will it hit the ground? So we want y of t to be equal to 0. Well, y is equal to 500 sine 30 degrees t minus 1/2 of 9.8 t squared. Simplifying this, sine of 30 degrees is 0.5, so we get 250t minus 4.9t squared. And we want that to be 0, right? We want 0 to be equal to 250t minus 4.9t squared. And we can solve this by factoring, or the quadratic formula, or completing the square if you really want to. But I'll just use factoring. This factors as t by 250 minus 4.9t. And so setting each of those to 0, t equals 0. That's when it was fired. Or 250 minus 4.9t is 0. And solving that second equation for t, we find that t is about 51.02 seconds. And that's when the bullet hits the ground. How far from the gun will it hit the ground? We know it hits the ground in 51 seconds. How far away from the gun is that? Well, that's an x coordinate. And so we want to find x of 51.02. X of 51.02, that would be 500 times cosine of 30 degrees times the time, which is 51.02. And so if you go through all that, you should find it's about 433.01, and that would be in terms of meters. So it'll hit the ground 433 meters from where it was fired. Oh, hold on. That is incorrect. The 433 times 0.01, that's just 500 cosine 30 degrees. We still need to multiply that by 51.02. And multiplying that by 51.02, that's more reasonable. It's about 22,100 meters. So 22 kilometers. That's much more reasonable. What is the maximum height reached by the bullet? Well, maximum height. Well, we know the height function, right? We figured out that the height function, y, is equal to 250t minus 4.9t squared. So when is the height maximized? Well, that sounds like a calculus problem. Y prime would be 250 minus 4.9 times 2 times t, calculating the derivative. So that's 250 minus 9.8t. And so then we set that equal to 0. And solving, we find that t is equal to 25.51 seconds. So, and we can verify, though, using the second derivative, we see that the inflection is down, and so we know that that's a maximum. So then t, we know that this is when it reaches maximum height. But we're asked for the actual maximum height of the bullet. So now we calculate what is y of 25.51. And y of 25.51, that would be 250 by 25.51 minus 4.9 by 25.51 squared. And that's about 3,190 meters. That's the max height. Alright, so there's an example of how parametric equations are used in motion. And that was a fairly simple example. So now we're going to go in the other direction. Before, we started with the parametric equations and drew the curve. Now we're going to start with a curve, or some sort of context, and try to write the equations. So here we're asked to write parametric equations that describe a line passing through 0, 2, and 7, 5. Well, now, you learned how to write the equation of this line back in, like algebra, an algebra course. We could write the equation of the line as y equals, let's see, the slope is 3/7, and the y-intercept is 2, so 3/7 x plus 2. All right, so where the slope m was what, delta y over delta x, and so 5 minus 2 over 7 minus 0, that's 3 over 7. All right, and the y-intercept is 0, 2, so that's the b value. But this isn't a parametric equation, this is a Cartesian equation. All right, so very important. In general, if we have y as a function of x, then we can write that x of t is simply t, and y of t is f of t. And that would describe the parametric equation for the Cartesian equation. All right, so we can just replace x of t with the parameter, and then y of t is the function at t. So the parametric equations that we can use are x of t is t, y of t is 3/7 t plus 2. That's one approach. An alternative approach, so that's one correct answer. Here's a second correct answer. And in this approach, for a line, this will only work for a line, we can write x of t is the initial x value plus delta x t, y of t, I shouldn't be using subs there, I should just be using ofs. So we have x of t and y of t is y sub 0 plus delta y t. This will only work for a line. So I could write then that x of t is the initial x value, which is 0, plus delta x, that's 7, times t. I can write that y of t is the initial y value, which is 2, plus delta y, 3t. And this will describe this. Either of these parametric equations will describe that line. What if we were asked to, instead of writing parametric equations for the line, now we only want the line segment. So now it's got to stop at that initial and terminal point. Well, we can use the same equations, we just now have to put limits on the parameter. So I could have x of t is t, y of t is 3/7 t plus 2, and I can just take those and add the restriction on the parameter that t goes from 0 to 7. And notice that if t is 0, we get the first point, right? If t is 0, we would get 0, 2, and if t is 7, we would get 7, and 3/7 of 7 is 3, plus 2 is 5. So we can easily verify that. If we used the other situation, so if I said, okay, if we use x of t is equal to, 7t, and y of t is 2 plus 3t. If we use that other situation that we can use only for lines, what's nice about this one is that for this, the parameter goes from 0 to 1. And sometimes that's very nice. In later courses where you will have to parameterize certain graphs before you do something else with them, you're going to need, it's often useful to have the parameter go from 0 to 1. It makes life a little bit easier usually. What if we took the line segment and reversed it? Right, so notice we're changing the direction here. Well, to change the direction, notice that now the delta x would be 0 minus 7, which is negative 7, and the delta y would be 2 minus 5, which is negative 3. So I'm going to use that second idea, and I can say then that x of t is 7 plus delta xt, so minus 7t. And y of t is 5 minus 3t. And I'll have the parameter go from 0 to 1. Write parametric equations that describe the circle centered at the origin with radius 3 traced counterclockwise. So this is the situation that I described earlier, and so then we would have x equals 3 cosine t, y equals 3 sine t. How would we make it trace clockwise? To make it trace clockwise, all we need to do is change the sign, S-I-G-N, on the y. So adjust the sign to a negative 3 sine t. And let's just double check that one, just to be sure. Alright, so go back to my y equals. Let's change this to a 3 cosine. And I'll change that to a negative 3 sine t. And let's just verify this, that it does go around the circle clockwise. Alright, so let me graph it. Alright, it does go around the circle clockwise. Now, if we only want to trace the curve once, then we would add on the parameter t is less than or equal to 0 to 2 pi. That will trace the curve around once on either of those. Really, if we don't put anything on the parameter, if we don't tell anything about the parameter, it just keeps on going around and around in that circle as many times as we need it to. If we only want it to go around once, we put the stipulation 0 to 2 pi. What if we want instead the semicircle centered at the origin with radius 3 traced counterclockwise from 3, 0 to negative 3, 0? Alright, so just drawing a rough sketch. What we're talking about here is that figure, right? From 3, 0 to negative 3, 0 traced counterclockwise. Well, that would be the same equations. X equals 3 cosine t, y equals 3 sine t, but we would put on the restrictions on the parameter from 0 to pi instead of 2 pi, and that would get us halfway around the circle. Now, what if we want the parameter to be 0 to 1 instead of 0 to pi? So what this is saying is we want our initial point now. Right, so if we want this, what we're saying is that this point is associated with t equals 0, and this point is associated with t equals 1 instead of pi. So how do we get around, halfway around the circle in 1 second rather than pi seconds? All we do there is change the argument of the function. Instead of a t, we need to change that to something else. So what do we change it to? Well, we want to go, if we just think normally, we're trying to go from 0 to pi. But we need to get to pi in 1 second. So what I'm going to do is, I'm going to multiply t by pi. And notice that if t equals 0, then we would have cosine 0 and sine of 0. which starts us at our first point. And if t equals 1, we would be evaluating cosine of pi and sine of pi. So this is really just sort of adjusting, if you remember the period of a sine function or a cosine function, this is very closely related to adjusting the period of that cosine function or sine function. Alright, so now we're going to put some ideas together. We're going to try and write parametric equations that describe this figure. Now, you won't be able to do it in just one set of equations. So instead what we're going to do is we're going to write two sets of equations that describe this curve, and we're just going to adjust the time, the parameter. So what I'm going to say is that this is going to be this point is t equal to 0. This point will be t equal to 1, and the third point is going to be when t equals to 2. Alright, so first thing I'm going to do is I'm going to write an equation for this semicircle. Notice that it's centered at negative 2, 5, right? That's the point negative 2, 5. It has radius 1, 2, 3, 4, right? The radius is 4. Alright, so from 0 to 1, notice it is going clockwise, but it's starting at the right-hand side. I'm sorry, at the left-hand side. So if I started with x equals, x of t is 4 for the radius, cosine t, and y is 4 sine t, I know that that describes a circle, but it's going to be centered at the origin. Alright, so let me adjust it. I've got to shift it to the left and up. To shift it to the left, I'm going to subtract 2 on the x. So negative 2 plus 4 cosine t. To shift it up, I'm going to add 5 on the y. So 5 plus 4 sine t. But now if I did that, remember that would start, if you remember what we've seen with writing the parametric equations for circles, that would start at the right-hand side and traverse counterclockwise to the left. And that's not what we want. We want it to start on the left-hand side and go counterclockwise. So what we'll do is we will adjust the cosine. We want it to flip to the other side, so we're going to make that a negative. Now that'll start it on the left, but if we keep this as a plus 4 on the sine, it would move up. It would start moving clockwise instead of counterclockwise. So we'll need to adjust that as well and make that a negative. Now, if we just leave it as a t for the cosine and the sine, what that will do is that'll complete the circle over 2 pi units. But we want it to go from 0 to 1. So like we did before, since it's a semicircle, we will make it a pi t. Now let's just check that part. And we want this to be from 0 to 1. So let's check that part on the calculator. Alright, so y equals, y1 is negative 2, I'm sorry, x1 is negative 2 minus 4 cosine pi t. And y1 is 5 minus 4 sine pi t. And let's have this, our window go from t is 0 to t equals 1. Let's verify that we've done this correctly. And I'll graph it. All right, and that looks pretty close to what we want. We can, of course, trace this if we'd like, F3 to trace, and it'll start at t equals 0, and that gives us the point -6,5. That's good. And let's just check if we can get to t equals 1. Will it let us go? No, it won't let us go to t equals 1. Type it in directly, and at t equals 1, it gets us to 2, 5, which is also what we wanted. So that's good. All right, now, how about the other part? The other part's easy. We're going from t equals 1 to t equals 2. So the first point, well, let's see, that point is what, 2, 5. And at t equals 2, we have the point, what we want to go to 8, 0. So let's see, my delta x, my change in x is 6, and my delta y is -5. So my first x would be, let's see, x of t would be 2 plus 6t, and y is 5 minus 5t. Now this was okay if t was going from 0 to 1, but we have t going from 1 to 2 now. And so what we need to do is adjust our t. We have to write it as t minus 1. Right? Because we've kind of shifted our time by 1 second. And now we put on the parameter from 1 to 2 seconds. Let's check that in the calculator as well. So back to my y equals screen, and we'd have 2 plus 6, quantity t minus 1, and 5 minus 5, quantity t minus 1. All right, and I'm going to turn off x1, y1, and let me adjust my window to go from 1 second to 2 seconds. And we'll graph that. And that looks reasonable. Again, I'll go ahead and trace this. And it has the first point correct at 2, 5, and I'll just type in 2, and we do get to 8, 0. So those two sets of parametric equations will describe that figure. All right, that concludes the presentation for this section.